won't be able to check. He won't be able to do exhaustive search or whatsoever. Okay, he is limited on that. Okay, and this limitation, once it is taken into account, you can build pseudo-random sources deterministically. That's the main idea. Is that you can find things that looks random, okay, but which are not random, so do not have a high complexity because they are generated by polynomial time algorithms, okay, but are more random than a stupid sequence because they are able to fool any polynomial time algorithm. Okay? Okay, so I won't tell you how it's made. Okay? I will just tell you a little bit about how we can hope that it exists. And why is it interesting? So, first, why is it interesting? Is that basically, you know this thing about Poincaré and chaos theory, is that, you know, the randomness output from some chaotic systems is random enough for us. Looks random enough for us. Looks random enough for any need we have. Okay? So for instance, if you imagine that nature is a polynomial time algorithm, okay, because you don't wait forever until when your body grows, okay, you won't wait an exponential time until they decide to build a new cell. Okay, the cells are growing all the time. Okay, so it's a pretty fast process, the biological process, for instance. Okay? Basically, how much complexity do you need to have randomness in your system? You know that randomness is a key in biology. You need randomness for selection, for Darwinism is all based on randomness. You know, you select, the evolution is based on randomness. If you don't have randomness, you don't have evolution. Okay? So, basically, the question here is, you know, the problem we had before is define how complex an object is. Okay, so let's focus, for instance, on the chaotic systems, on the randomness output by your chaotic system. Is it really complex? Okay, so it turns out that if this output of the chaotic system can fool any polynomial time machine, like your body, then it's random. Okay, it's random enough because you get the exact same distribution as when it was eating some random bits, truly random bits. Okay, so you get here a kind of way of measuring whether your string is random or not. So these are ongoing research. I mean, the result I will evoke with you are results that are 2 years old, more or less. Okay, but I think that this is an important step towards the definition of truly useful complexity, something which is truly useful. So, what I mean by that is that if you imagine that here you have your human body and here some chaotic systems that is used as a random source to your body. Okay. Basically, here what you have is that your pseudo-random source is exactly deterministic chaos. Okay, it's a definition of deterministic chaos in some way. These pseudo-random sequences. The pseudo-random sequences are exactly the one that can fool any systems that is not too powerful. Okay, this is exactly deterministic chaos. We know that it's deterministic, but we are unable to tell whether it looks random enough for us. Okay, for instance, it's very useful that some stupid sequences like the one that we used, you know, when you call random, it's nothing like random in computers. There is no randomness in computers. The random numbers, it's a sequence that is known to have some fairly good properties. It's basically, usually, it's just a multiplication modulo some prime numbers. So basically, you know that x, if r n plus 1 is the output, if rn is the output of a random function when you call it for the n of time, okay? Clearly, what's going on in your computer is that r n plus 1 is just a times rn plus b modulo some prime number p. Okay? That's how the random numbers are generated in your computer. Okay? So this is definitely not a random sequence. Clearly not. Even if you start from a random seed at the beginning, if R0 is uniformly random, you see that there are huge correlation between Rn plus 1 and Rn. Okay? But it turns out that it has good enough properties that for the purpose we have. Okay? So one of the nasty things when you do cellular automata, for instance, is that it will at some point cycle. Okay? And with cellular automata, when you're iterating over a matrix of size 100 by 100, for instance, it will cycle within 1,000 iterations. So, it's not that good. It depends on your purposes, but for most of the purposes, except cellular automata, it's good enough. Okay? So, the problem is defining what good enough is. Okay? And this might be a good definition. I mean, but good enough is just fooling everything that we can do in reasonable time. Okay? So now, how can we do that? So this is a pretty nice definition, okay, but it's totally hard to use, okay, because it has to work for all polynomial time algorithms, so it's completely crazy. How can I hope to generate this kind of sequence? So what they did first is that they defined unpredictable strings. Unpredictable strings are random strings. By random, I do not say uniformly random. Okay, I just say random. Okay, so for instance, the string all 0 or all 1 with probability 1/2, 1/2 is a random string of length n. Okay, I have only two choices, but the output is random. Okay, that's exactly what I mean here. You won't get all the outputs, okay, but you will get a subset of the outputs, but it's a random subset. Okay, so it's a random string where if you give the I first bit of the string to a polynomial time algorithm, it won't be able to guess the next one with probability significantly larger than 1/2. Okay? So this is how you define a predictable string. So this is somehow easier to manipulate. Okay? But this looks a little bit weaker than that. Okay? Because here you assume that you know already the I or stronger. Weaker or stronger? Maybe stronger, I don't know. It's not easy to see that whether it's stronger or weaker than the other one. Okay? But it's a reasonable one. And it turns out that in a sequence of papers, here, turns out that pseudo-random strings are exactly unpredictable strings. And the proof is quite nice. And the most interesting thing is that proving that obtaining these strings, being able to produce this kind of strings, that means to produce deterministic chaos, is equivalent to conjectures, long-lasting conjectures in computer science, like P equals NP. So, why do I mean P equals NP? Is that because in order to generate something that looks random to polynomial time algorithm, basically, intuitively what you need is something which is really hard to compute. If you have something which is really hard to compute, then everything that is output by this function will look random to a polynomial time algorithm. Does it seem reasonable to you? But I'm sure that nobody understands what I'm saying. But in fact, it's for me that I'm teaching. It's for me to understand better what I'm saying. But anyway, I'll try to do it well. So basically, what we want to do is being able to generate deterministically. We want to generate deterministically a long string that looks random to any polynomial time algorithm. Okay? So, basically to do so, we will